All right, how's it going? My name is Travis Growthhouse, and this is for the ME302 final with Professor Andrew Keen. I'd like to point out that my test is actually annotated to heck and back because I actually have a brain injury from the Army, and if I don't write things down, I'm just gonna forget things like mid-sentence. So that's why it's written up so much. But I got my final here, and then so we're just gonna go through this. All right, so starting out with problem one. We've got the PV and TS diagrams. I'm not going to spend too much time discussing these because they sort of take shape as the problem moves on, but some things to keep in mind as we look at them is because we know a couple of the processes are adiabatic and reversible, we have a couple isentropic processes which are represented as vertical lines on the TS diagram where delta S is equal to 0. We're also given a couple phases such as saturated liquid and saturated vapor, which can be found on either side of the vapor dome, so we're going to be using those. And those are some main things to point out. So moving on to part C here, we are starting with the energy balance for an open system. We've got a diagram of a turbine on the right, and whittling this equation down because we know that it's steady state, adiabatic, there's one inlet and one exit, and that the potential energy and kinetic energy changes are minimal. We can actually will that down to work equals mass times H1 minus H2. So from here, we actually move on to the next stage where I'm finding all my properties. So we're going to move down from that because we don't know H1 or H2 at this point. So at state one, we know that because we're given pressure and that we're told that it's a saturated vapor, that means that we can find this on the liquid, the liquid vapor tables. And it's going to be all the way over to the right. So we can find that line, we can trace it all the way, and H1 is equal to Hg, which can be found on that line. And then with that, I actually wrote down a couple additional values because I figured we need them, but S1 is also equal to Sg, and V1 is equal to Vg. From that, we also get the temp, which is 311 degrees Celsius. So with that H1, which we just found, looking at the TS diagram, we know that S1 is equal to S2. S1 is equal to S2 because it's an isentropic process. So with that, we have S1, so then we go and find S2, and we see where that sort of lies in between, and from there we interpolate back to find H2. And so, yeah, we find H2. And so with H1 and H2, we're able to plug that back into the original equation, a page up, and then we get the answer there. So we're going to move down to the next page, part D. So once again, we start with the energy equation for an open system. We whittle it down, same thing, steady state, adiabatic, one inlet, one exit, and then potential and kinetic energy equals 0. Here I got a little bit mixed up because I'm pretty sure I'm supposed to be using that equation on the right to find the H value for a compressed liquid. I think that's what you're supposed to use. I got a little bit mixed up here, and I wasn't too sure how to use it. So ultimately for this part, I just decided the two values were going to be close enough for an approximation. It's not going to turn out perfect in the end, but I ended up using H3 equals H4 just because I wasn't too sure how to use that thing on the right. So I ended up with work equals 0 for this. I think it almost makes sense because the area under the curve on the PV diagram for 3 to 4 is going to be extremely tiny. So I think the work is going to be extremely small anyways. So I know it's not 0 because that doesn't make sense, but I didn't know how to use the equations. That's what we ended up going with here. Okay, so moving on to part E. Same thing, open energy equation. With this one, it's got all the same things that we whittled down, except we remove work this time because there's no moving parts in a heat exchanger. That's what we were taught in the last time I took this class, no moving parts equals no work. But also the formal definition is because it's an open system, we integrate VdP, and because there's no change in pressure across a heat exchanger, that equals 0, so we can remove work from that. So similar to the last one on this one, we end up with the equation Q equals M times H1 minus H4. I wasn't too sure how to get H4 in this situation, but I think it has something to do with doing something with S3 equals S4 because of the isentropic process. So I kind of left it with that, but I think I'm onto something good there. Moving on to F, which is where I get back on track. So once again, heat exchanger, so no moving parts, or integrating VDP equals 0 because no change in pressure across a heat. No change in pressure across a heat exchanger. Whittling down all the same things. And that one was pretty straightforward because we have H3, which I think was what I estimated to be the same as H2 in the previous one. Yeah. So that's why I ended up with the heat. So then moving on to G, I wasn't able to finish this one just because I wasn't able to get Q in on the last one, which is part E. But I know that for the thermal efficiency of this type of system, we're going to be using this equation, and it ultimately comes down to the work of the turbine minus the work of the pump over Q in. And so I have the two works, but I just wasn't sure what Q in was. So I just wasn't able to do that one. Okay, moving on to H. So we're talking about maximum theoretical efficiency, and for that one, it is the efficiency of a reversible cycle, which is 1 minus Tc over Th, which I have those converted to Kelvin because we need that in absolute because it wouldn't make sense in Celsius. And I ended up with a maximum thermal efficiency, so maximum optimacy of 42.9. And so although I don't know the answer to the previous one, I know that N reversible is always going to be higher than N actual. And that's because there's going to be actual heat loss in real life, and none of these things are going to be perfectly adiabatic. So we are going to lose some of that heat to the surrounding environment. Part I didn't even want to pretend like I knew what I was doing to that one, so I just skipped that one entirely. All right, so moving on to the conceptual questions here. A, so we started with the first law of a closed system, and because we know it's an ideal gas, so U and H depend entirely on T in an ideal gas, and because it's isothermal, there's no change in temperature, which means that U1 is equal to U2, so we can get rid of delta U. Then we move the W over, and we end up with Q equals W. And so we know that with the expansion work of a closed piston cylinder, the work is always positive. So with that, with Q equals W, if W is always positive, then Q is always positive. So it's positive. B, we discussed this in a lecture. Same thing with putting an air conditioning and leaving it in the center of a room. Although it's going to be taking that cold air and blowing it out the back, sort of evening itself out, there's always some heat loss in the processes themselves, so the overall room is going to be heating up the entire time, so it's going to act as like a heater. C, we know that irreversibilities increase entropy, so the delta S of an irreversible cycle is always going to be greater than the delta S of a reversible cycle, and that's because irreversibilities increase entropy. And yes, you can reduce the entropy of an entire system. You just can't reduce the entropy of the universe. And so an example of that is you would get a negative change in entropy by cooling something off. And then E, very simply put, is because energy is a property. So for F, once again, it's irreversibilities increase entropy. So the sigma of a reversible cycle is equal to 0, while the sigma of an irreversible cycle is greater than 0. That's why you can never get a negative sigma. Intensive properties are just pressure, temperature, and specific volume. And H, I didn't really solve this one quantitatively, but I'm going to walk through it anyways. So we're starting with the open energy equation for a turbine. We can whittle it down because it's given that it's adiabatic, so we're getting rid of Q. Steady state, so the equation on the left goes away. And then so I got rid of the changes of potential and kinetic energy here because in one of the lectures we discussed that for gases in a turbine, the changes of kinetic and potential energy are so minusculely small that they actually don't matter. So if we were to solve this quantitatively, leaving those in, I imagine that if you put all of that in there, so it'd be the additional phrase would be VF squared minus V initial squared for velocities over 2. If you threw that in there, I imagine it'd be so small that it wouldn't really even be worth mentioning. Okay, so problem 3 was a bit of a doozy as we step our way through there. Same thing, PV TS diagram sort of takes shape as the problem goes along. Some of our assumptions were, well, some of these aren't really assumptions. We're told ideal gas, variable specific heats, and then no change in potential or kinetic energy. So moving on to process 1 to 2 here on the right, I sort of sketched out those individual processes so you can see them. So with the PV diagram, so the area to the left is the work on that curve, while the area under the curve on the TS diagram is the heat transfer for mass flow rate. And so with TS, because we know it's the area under the curve, that turns out to be 0. And so for the work, we start with the open energy equation. We whittle everything away because steady state, adiabatic, 1 inlet, 1 exit, get rid of the potential energies, and we're left with that equation, H1 minus H2. And so with that, we can find H2 on the ideal gas, which is the ideal gas table at A22, because we have the pressure and we know it's an ideal gas, so we can just find that H2 and S super 2 because of that. And so now with that, we need to find a way to find H1 because we don't have that yet. And so what I decided to do was I used the equation for the isentropic process for an ideal gas with variable specific heats, and it's the rather disgusting looking equation with the S superscripts. And what I did was, because we know it's an isentropic process, the left half, so delta S is S2 minus S1, that equals 0. And so with that, we have S super 0 at the second temperature. We don't have S super 0 at the first temperature, but then we have R bar using the values in the book for the molecular weight for air and all that good stuff. And then we have pressure 2 and pressure 1. And so with that, we can solve for S super 0 at temperature 1. And with that, we go back to table A22. We find what temperatures it's between. And in this case, we found out it's between 490 and 500 Kelvin. And so with that, we can interpolate back from the S super zeros to find H1. And that's how I found H1. And so from that point, we have H1, we have H2. We plug it in to find work. So moving on to process 2-3, which is kind of broken down into 2 steps. I started with the open energy equation, whittled it down. With that, I realized that I wasn't too sure how to get H3, but I had H2 from the previous problem. And I was stuck on this for a bit, and then I realized that problem 3-4 is very similar to, or process 3-4 is very similar to process 1-2. So I skipped ahead to process 3-4 and left process 2-3 behind. So we're going to skip ahead to the next page. And this one is very similar to process 1-2, open energy equation, and I did the exact same steps using the equation for isentropic processes with ideal gas and variable specific heats. We have S superscript, or S super 04 based on state 4, which is locked in at a pressure and a temperature. So we go to the ideal gas once again, and we find that S super 04. We plug that in the left side, so the delta S's are equal to 0. And from this point, we're trying to find that S super 0 at temperature 3. We have the updated pressures, but we keep the R values the same. And very similar to process 1-2, we interpolate back through table A22 because we figure out that S super 03 is between 690 and 700 Kelvin. So we interpolate between all that to find H3. And so with that, we actually have everything we need to solve this process. So process 3-4. So going back up to the PV and TS diagrams, once again, TS, we know that the heat transfer per mass is under the TS curve, which is 0. And then we're able to plug in H3 and H4 into the work equation to find the work. And so that's solving that one. So now that we have H3, we actually are able to go back up into process 2-3. So we found H2 in the first process, we found H3 in the third process. We have both of those. And so we plugged them into the equation, which gets us heat transfer. And then also looking at the PV diagram, we know that the work is the area to the left of that. And so that's 0 because it's a horizontal line. So with that, we have process 1, 2 solved. We have process 2, 3 solved. We have process 3, 4 solved. And moving on to process 4, 1. And so we have H1 from the first process and we have H4 from the previous process. And so we're able to solve for heat transfer. And once again, the area to the left of the PV diagram is work, and that's 0. And so now we've solved for heat rate and work rate for all the processes. So we're moving on to step 7. Very simple equation for this one. It's the coefficient of efficiency for a heat pump is gamma equals Q dot over work cycle. And so there's only 2 processes of work, so we add those up. And then QH is always negative. So that was, which one is that again? So process 4.1 is the QH that we're plugging in, and we end up with a efficiency of 2.6. And so moving on to the final part, step 8, I also wasn't even going to take a stab at this one because I don't know how to do this one either. And that pretty much wraps up my final. Thank you very much. Rate, comment, and subscribe.